All right, well, thanks for coming, everyone. Like Clint said, I'm Brian, and I'm a software engineer on the Vault team at HashiCorp. And today, I wanted to talk about two of the newish features in Vault, one of which is Vault Replication, which is the newish feature. It came out in Vault 07, and some more functionality around it came out in Vault 08. And with Vault Replication, I'm going to talk about the distinction between high availability and replication. Then I'm going to go into some of the different ways you can use replication, and then get into some of the ways that your secondary might act when it's in a replicated state. And then after that, I'm going to talk about the new Kubernetes auth backend that we announced yesterday at the keynote. And I'm going to just go through how it works, and then I'm going to do a quick demo of it running in a Kubernetes cluster. So first, we'll talk about Vault Replication. And the distinction between the high availability feature of Vault and the replication feature of Vault is that high availability has been around for quite some time in Vault. And it's available in the open source version. And in high availability, clusters are active in standby. And so you have one active node and one or more standby nodes. And when if the active node goes down, a standby can take over leadership and become active. And so this is a feature that allows the minimization of downtime. And all the nodes in this HA cluster actually talk to the same underlying storage backend. So they're all configured to talk to the same console cluster or Postgres database. And replication, which is an enterprise feature, came in Vault 07, is a has primary and secondary clusters. So each of these clusters can be an HA cluster. And each cluster has its own storage backend. So the primary cluster and the secondary clusters talk to two distinct, diverse storage backends. And all the data from the primary is replicated down into the secondary. And so there's a few ways that you can run replication in your system. And we call these replication modes. And so the first mode I want to talk about is the performance replication mode. And performance replication is used for scaling horizontally static secrets and other configuration. And that's kind of a loaded term, but that really just means that secrets in the generic secret backend and your configuration for your dynamic secret backends will replicate down to a secondary cluster. And that essentially means that things like retrieving static secrets from your generic backend or doing things like transit encryption can scale horizontally across multiple data centers. In performance replication mode, updates to the primary and any of the shared state, so shared secrets or the configuration for them, has to be managed by the primary. And so write requests are automatically forwarded back to the primary. And so performance mode isn't meant to scale write requests. It's only for scaling read requests across multiple data centers. And in this mode, some items are local to the local Vault cluster. So things like tokens and leases, so your authentication token with Vault and leases for secrets don't actually get replicated to the secondary. And so it's recommended that any application in a data center talks to its local Vault cluster so that it doesn't have to authenticate to multiple clusters. And so you're not talking across to another data center. So the next mode, which came in Vault 08, is performance mode with mount filtering. And what this allows you to do is use performance replication. So you're scaling those secrets horizontally. But it also allows you to add granularity to what secrets get replicated where. So for example, you can set up a mount filtering rule and not allow your transit encryption keys to be replicated down to data center 3. And you would do this if you weren't expecting to use transit in data center 3, but you are in data center 2, for example. And so this feature works with whitelists and blacklists, and helps you to comply with data movement and sovereignty regulations. And then the third mode, which also came in Vault 08, is called disaster recovery mode. And this mode is used to help to recover from a loss of an entire cluster. And so in disaster recovery mode, every piece of data that's needed to fully restore the primary cluster is actually replicated down to the secondary. So this includes local items like tokens and leases, and can actually be used in conjunction with performance replication. And when a secondary cluster is in DR mode, it actually doesn't handle client requests. So it's just sitting there waiting to be recovered in the event of a DR scenario. So that was kind of a lot of information, but hopefully this diagram helps to clear up kind of how these things can be used in conjunction with one another. So in this example cluster setup, we have performance primary in data center 1, and that's using performance replication to send its secret and secret configurations over to data center 2, where we have a performance secondary cluster. And then in each data center, we have a disaster recovery cluster that the performance clusters replicate down to. And so if in either of these data centers we lost our performance cluster, we can use the DR replicated cluster to promote them and use them to recover our primaries. And it's worth noting that DR is just that. It's a used for disaster recovery. We still recommend using some kind of snapshotting tool of your storage backend. And so if we were to write a secret to the performance primary here, the first step in replicating all that down to each data center would be, first it would commit that information to the primary, and so it would store it in its storage backend. And then the second step would be the primary replicating that down to its DR secondary and the performance secondary that's in data center 2. And then the third step would be the performance cluster in DC2 would save that to its storage backend and then replicate it down to its DR secondary. And so now we have secret foo living in our 4 different clusters, 2 of which are for serving up that request, and 2 of which are for recovering in case we lose one of the primaries. And so now if we lost the performance secondary, there's currently now not an active Vault cluster in data center 2. So the applications data center 2 don't have a Vault cluster to talk to. And so to promote this DR secondary and make it into a primary, we run this promote command, and this command actually takes the unseal keys that you have with Vault. And so it's a privileged action. You need to get your unseal key holders together to do it. But because the secondary had all the information that the primary had, when it comes back up, it knows exactly where that primary is, how to connect to it, what the authentication method is for it, and it's able to reconnect to the primary and start getting updates that it might have missed. And because the secret foo that we just wrote was already replicated down to the DR secondary, when it came back up, it was right away able to serve that request. And so any application that's running in Data Center 2 would need to be able to handle this case. So your service discovery would need to know how to recognize that the new active cluster is at this location. Okay, so those were the different replication modes and an example way to set them up. And now I want to talk a little bit about different states that your replication secondary can be in. And this is different than modes because regardless of mode, your secondary is going to be in one of these 3 states. And these states are streaming wall mode, Merkel Diff, and Merkel Sync mode. And these are all different ways that your secondary gets up to speed with the primary. And I want to run through them really quickly, and I think it's important to know what's happening in each of these modes because it says something about the state of your secondary cluster. And so if you're running a replicated cluster and you inspect the state of your secondary, it'll be in one of these modes, and that means something different. And so before we jump into each specific mode, I want to first really quickly cover what are these things? What is a wall and what is a Merkel? And to do that, I'm going to just walk us through everything that happened, or most things that happened between writing a secret to data center 1 and it getting replicated down to data center 2. So if we write a secret to the primary, the first step in getting that to the secondary is it uses a write-ahead log. So a write-ahead log is a way to guarantee that the update is logged in the correct order. And so, sorry. So every key that's updated or deleted within Vault also just adds something to this write-ahead log. And these are very commonly used in a lot of databases. And so every time we want to write one of these write-ahead log entries, we use transactions to guarantee that it gets written at the same time as the actual key update. And the write-ahead log is used in streaming wall mode and a lot of other places within replication that we won't cover in this talk. And so after we write the write-ahead log and commit the information down into the secret backend, or storage backend rather, sorry, we will then add it to Vault's internal Merkel tree. And a Merkel tree is a handy data structure. It's commonly used in a lot of databases or used in cryptocurrencies fairly commonly. And it's a nice data structure because it really efficiently and easily keeps the state of an entire data store. And so every time a key is updated or deleted within Vault, it's also updated or deleted in this Merkel tree. And so the way Merkel trees work, oops, no way. Yeah, so the way Merkel trees work is if we add a hash into the Merkel tree, if we add a new key into the Merkel tree, Merkel trees, the parent of a node is the hash of all the nodes below it. And so if we were to add this new key with a hash, the parent of that data shard will update its hash to include that new key. And we'll keep going up the tree so that then its parent will update its hash because the children nodes updated theirs. And we do that all the way up to the root node. And this is called the Merkel root. And because the Merkel root is the hash of everything below it, it's a really easy way to compare two states. So the Merkel root encompasses the entire state of the entire data store. And that's very helpful when sending information down to a secondary. And so after we commit the wall log and the Merkel root, we actually just put those into an in-memory list that keeps the right order. And so every time a new key is updated, we'll add it to this list. And we call this the log shipper. And it's worth noting that so far everything we've talked about is happening internally in the replication primary. And so we actually haven't sent anything over to the secondary yet. This is all just still getting to the actual sending of data. And so now, if you were to inspect your replication secondary, if you were to run this sysreplication dr status, we're going to check the status of our dr cluster. And we see that it's in mode dr secondary, which seems right. It's supposed to be a dr secondary. And then we see that its state is the streaming wall. It says streaming walls. And that means that we're in streaming wall mode. So when a new secondary connects, it does so over this mutually authenticated TLS connection and attempts to join in streaming wall mode. And what that means is the secondary tells the primary what its current state is, so it shares its Merkel root with the primary. And then the primary can use that to look backwards in its log shipper to find if it has a match. And so if it finds a match, it means the location here where the hash equals 82ECB4, that thing, it means that at that point in time, the two clusters were the same. But since the primary has gotten 4 more wall entries update. And so the primary will then send those 4 wall entries down. And after sending them down, the primary and the secondary should be in the exact same state. And so the streaming wall process will actually sit here and block and wait until the next entry is sent and updated, and so on and so forth. So your secondary is always sitting in this state where it's just receiving the newest update from the primary. And this is a really good place for your secondary to be in. It means it's up to date, or it's very close to being up to date, and it's catching up. And so the next replication state that you might find your secondary in is Merkel Diff state. And this usually means that your secondary is too far behind. It might have been shut down for too long, or its state is not able to be recognized by the primary. And so its data is out of sync. And this is a less desirable state for your secondary to be in. It means it's going to need to go to the primary and compare its state. And so this is the Merkel Diff mode. It's just the secondary saying, hey, I'm not able to join in streaming wall mode. Let's do a diff. So another nice feature of Merkel trees is they're really easily and quickly diffable. And so if we were to diff these two trees, we would compare their root hashes, and then we'd find that they don't match up. And we'd compare all their children, and we'd find that these 2 children on the left here didn't match up. And we'd continue down the tree, checking the children of that node, finding that these 2 didn't match up. And then we'd compare the underlying data shards and see that the primary has this extra key and this extra bit of data that the secondary doesn't have. And so the outcome of the Merkel diff is a list of all the differences between the 2 clusters. And so after doing a Merkel diff, and your secondary now has a list of all the things that it needs from the primary to catch up, it switches into Merkel Sync mode. So if you do a dr status command here, we see that the state is now in Merkel Sync. And this means that the secondary is reconciling itself with all those differences that it just got from the primary. And depending on how many diffs there were, your secondary might be in this state for a good bit of time, because it's going to the primary and downloading all the data that it needs. And so it asks the primary for each key update, and after it gets all the updates, the 2 clusters should now be in sync, and they can safely switch back into wall streaming mode, and updates will stream in from there. And this is all I had on the replication topic. There's obviously a lot more use cases, and I'd be happy to talk to everyone about that after, so if you come find me. Also, yesterday, Chandler from Adobe gave a really good talk on how they use vault replication in their system. And so if you didn't catch that, I recommend checking out his video stream. So next, I want to cover the new Kubernetes auth backend that we launched yesterday. And this came out in Vault 083, which was yesterday. And to build it, we worked in conjunction with the Kubernetes team to help design how it should work. And the way it works is it takes Kubernetes service account tokens. So service account is a form of identity within Kubernetes. And it takes that token and binds it to a few settings within Vault. So you can create a Vault role that requires information about the service account. So you can bind the service account name and the namespace that it's running in. And then Vault will also call back into Kubernetes and verify that that token is still valid. And so it uses Kubernetes Token Review API to do so. And the nice thing about this approach is it doesn't need any external pieces. It's simply Kubernetes internals, your application receiving things from Kubernetes that are built into Kubernetes, and then talking to Vault with a built-in auth backend. And so the way it works is within Kubernetes, you have a pod, and you can tell Kubernetes what information to give to your pod. So you set a service account on the pod, and Kubernetes will automatically mount that token into a volume, and it's actually a tempfs volume, so it's in memory. And your application that's running inside the container can just read that token from storage. So the step one in using this backend is simply going out to the local file system and grabbing the jot token. And then your container will use that token and make a call into Vault's API, and it'll send up the jot token, and it'll also send the role name that you previously configured. And Vault will validate that the jot meets the requirements of the role, and if not, it'll reject the authentication request. And if so, it will call back into the Kubernetes API to validate that the token still exists within the system and hasn't been revoked by an external party. And if all of that succeeds, then the Vault server will return a Vault token to your application that's running in the container. And so an example way to configure this backend is it's pretty similar to a lot of other Vault auth backends, if you've used any of them before. But you simply call Vault auth enable Kubernetes, and that will mount the backend at the path auth/Kubernetes. And then to configure the backend, we'll hit the /config endpoint, and we'll pass it some PEM keys that are used for validating the jot signature. We will also pass the Kubernetes host IP, or address, and then we'll also pass the Kubernetes CA certificate. And next step is we need to create a role. So the role is what actually binds service account information to a set of Vault policies. And so in this example, we create a role named demo. So you can see that up in the URL there. And we set the bound service account name to Vault auth. So our service account name is Vault auth. That's the one we want to allow to access this role. And we want to make sure that service account lives in the default namespace within Kubernetes. And so we set the bound service account namespace to default. And then after that, we can set some configuration settings and information about what that user should be able to do within Vault. And so we set a list of policies. So in this example, we'll set the kube authentication policy, and just to denote that this user is coming from Kubernetes. And then we can also give it information about the token. So we can say that we want the token to live with a period of 60 seconds, or we could give it a max TTL of something, or so on and so forth. And after we configure the role, we will call the Kubernetes login endpoint. And we pass in the role name, which is demo in this case. And then we pass in the JWT token, or JWT tokens in the name, that we retrieved from the Kubernetes volume. And so if everything succeeds, we should see an output similar to this, where it returns a Vault token as the first item in that list, and a bunch more metadata around your new token that you just got for Vault. And so I want to do a quick demo of a few applications using this new auth backend to authenticate to Vault from Kubernetes. And as a prerequisite, well, I'm starting the demo with an already set up Vault server, and the configuration I used to set up the Vault server, it was almost exactly the same as what I just had on the screen. So instead of doing it twice, I thought showing it on the screen was a better way to demo it. But OK, so in this demo, we have a Vault server running with a role defined as demo. And we have a Kubernetes cluster set up with no pods running currently. And so we have this file that defines a service account within Kubernetes. And it has the name, we give it the name Vault Auth. We say it's a service account. The namespace defaults to default. And so over here we can, also I have to look at this screen, which is kind of far away, so if I do any typos, shout at me. OK, so we created the service account within Kubernetes. And so now the service account exists, and we can start assigning it to pods. OK, so this is an example application. It's written in Go, and it's fairly simple. The application doesn't really do anything yet, but it could in the future. And it really just configures a Vault client right here. And then it reads the Kubernetes service account JOT token from the volume. And this is the default place that Kubernetes will mount the token. And then we make a call to Vault and hit the auth Kubernetes login endpoint. We pass in the role name that we created, so demo, and then we pass in the JOT. And then down here, we should, in the response, have a new Vault client token. And for demonstration purposes, I'll just log it out, and we can view it in the logs. Obviously, that's not something you ever want to really do in production. You don't want to output your secrets in the logs. So don't actually do that. And then down below, we'll just start a loop that will go on forever, and we'll just renew this token for as long as the application is up. And so that means the application can continue to use this token until it no longer needs it. OK, and so this is our Kubernetes deployment file. And it defines the container that we want to run. And a key important part right here is that we give it the service account Vault Auth. And then down below, we define the container we want to run. And this is just the application you just saw running. And we pass it the Vault address as an environment variable. And so I'll leave that up. And over here, we can deploy that deployment file. And so now if we read, if we get the pods from Kubernetes, we can see that we now have a running pod that has one container in it. And if we get the logs from that pod, we can see that we see the warning that we had printing out, and we see our Vault token right here. And then we see renewal is starting to happen. So every 20 seconds or so, the token will do a new renewal and keep it alive for another 60 seconds. And so the nice thing now is that your application has a Vault token and can then use that Vault token to do a lot of other things within Vault. And so you can use it to grab database credentials that your application will need, or you can use it to get a CA certificate to then bootstrap your HTTP server, and so on and so forth. So the nice thing is now that we have our Vault token, we can use all the features within Vault. And so we'll close out of there. And then I just had one other example application to show you. And this one, uses an application in one container and runs console template in a sidecar container. And so our application is actually pretty simple here. It just starts up, loads a configuration file, and down here we actually wait for that configuration file to exist. And once it exists, we'll load it and get some JSON out of it and store it and return it up to the main function. And then afterwards, we'll again log the information in it out to the logs, which again is just for demonstration only. And then the application will just sit and wait. And in this example, console template is actually the entity that's keeping your Vault token up to date. And so console template will automatically renew this token for you, and if the information that should go into the config file changes, it will also update that. And so here we just wrap console template with a very simple shell script. And all it's doing is loading the service account token from the volume. And then we pass the service account into this curl request that's hitting the Vault API and logging us in with the Kubernetes auth backend. And so here we can see that we pass the role name as demo and the JWT key as service account token, which we defined above. And then we run console template and pass it the Vault token, the Vault address. We tell it to renew the token that it gets, and then we tell it to use this template file and then add secrets into it and save it in this other location where our application can read it. So this is the config file that console template will use. Pretty simple. It just tells console template that we want to read the secret with the key secret/creds from Vault and store the information in this JSON blob. And so here we save username as the username that we get back from Vault, and we save password as the password we get back from Vault. And so this is the deployment file for this pod. And again, we give it the Vault auth service account name so that it can authenticate to Vault. We have two containers running. The first is our application, and then the second is console template that's using that shell script to start up. And then down below, we define a volume that both containers will actually use, and that's how console template will pass the config file from console template to your application. And we can define that this is an in-memory volume only, so it doesn't actually get written to disk. So over here we can read the pods again. There's still just one. And we run the deployment file. And now if we read the pods again, we can see that now there are two different pods running. And this one has two containers in it. And so now if we read the logs from that container, we can see that it output the warning that we were defining, and then say output username as demo and password as test, which it read from Vault, created this config file, and then passed it to our application. All right, and that's all that I had for you. Those are the demos. And yeah, thanks so much. I will be